This is Basic Optical Concepts, Unit 3, Diopter Power and Focal Lengths. Our problem here is, what is the focal length of a +3 diopter lens? And here I've drawn a +3 diopter lens. It's a convex lens. And whenever you're given a problem that simply states it like this, you can assume that you have parallel light striking that lens. And that will be important in a little while later on in this unit. When we looked at Unit 1, the math review, we studied reciprocals. And the reciprocal, as a reminder, is just taking any number, dividing it into 1. And essentially, if we're given this diopter power, if we want to find the focal length, all we need to do is find the reciprocal of this value. So the focal length of any lens, and it's going to tell you that it's going to come out in meters, is equal to 1 divided by the diopter power, or just the reciprocal of this. So 1 divided by 3, which will equal a plus 0.33 meters, and that's a repeating value. Notice I put the plus here on a focal length. That will tell me that the focal length or the focal point is to the right of this lens. Everything from here to the right is in positive value. Everything here is a negative value. So this plus sign ends up being important. It tells me what side of the lens the focal point is on. If I want to draw that to represent that, the focal length is to the focal point plus 0.33 repeating meters. This is Basic Optical Concepts, Unit 3, Diopter Power and Focal Length. This problem is, what is the focal length of a -2 diopter lens? Again, because of the way the problem was written, we are to assume that the light striking the lens to the left of the lens is parallel. And we have our focal length in meters is equal to 1 divided by diopter power, or just taking the reciprocal of this number, 1 divided into a -2, which is going to be a -1/2 meter. This is a convex lens, so notice I've drawn it with concave parts towards each other. This tells me, the minus sign tells me that the focal length happens on the left side of the lens. So what happens with light is it diverges as it enters the lens. And if I trace back the light rays on the left side, you'll see you have a virtual or theoretical focal point here of -1/2 meter. Virtual meaning that it never really does come to a focal point. The light rays actually just diverge and continue on. But if we were to trace them back, we would find the theoretical focal point of that lens. This is Basic Optical Concepts, Unit 3, Vergence Problem Demonstration. Vergence problem is when you have light striking the lens that is not coming into the lens parallel. You have here light source that's only 80 centimeters to the left of the lens. The lens is a 2 diopter lens, and what you want to know is, where does that light focus on the right side? Notice that because this light source here is so close to the lens, the light is actually coming off and diverging, and it's still diverging when it hits this lens. And if you look back in your class notes, all divergent light has a negative power, and all converging light has a positive diopter power. So it actually turns out that this light has a diopter power all of its own, so therefore it's going to influence how much this lens can bend the light when it comes out to the right side. So this is your typical 3-step problem. What we have to do is figure out how strong is this light diverging? How many diopters is this light diverging? And then add it to the diopter power of the lens, and then finally calculate where the inevitable focal length will be. If you remember a couple of demonstrations ago, I told you that everything to the left of the lens has a minus value. So that's our first thing, is we need to change this to a negative 80 centimeters because it's to the left of the lens. That corresponds with this diverging light. Diverging light has a negative diopter power, so this better be a negative distance. And this is actually a focal point. From the lens to this light source is actually a focal point. The other thing is, if you notice that when we did our finding the focal lengths of a lens and also taking and finding the diopter power using a focal length, we have to have this in meters. So this is given to us in centimeters. We need to convert that, and when we convert it, it ends up to be 0.8 meters. So now we're ready to use that in our equation. Simply take the reciprocal of this number, divide 0.8 into 1, and that'll give you the diopter power. So the diopter power of the light entering the lens is equal to 1 divided by a negative 0.8. And that will equal a negative 1.25 diopters. So that, I'll erase that. That light diverging to that lens is diverging with a diopter power of equivalent to a negative 1.25 diopter lens all on its own. So that's the diopter power entering the lens. So then I go to step 2. When that light strikes the lens and reacts with that +2 lens, what happens on the other side? Well, if I take the diopter power entering plus the diopter power of the lens, I'll find out how strong the light rays are when they exit the lens. So I take my negative 1.25 plus 2 is going to equal diopter exit. Adding unlike signs, you subtract and maintain the sign of the larger. So we're going to end up with a positive 0.75 is equal to the diopter exit. Again, this positive value here tells me that the focal point is going to be on the right side of the lens because everything on the right side is in positive. So I still have enough positive converging power of that lens to compensate for that negative power coming in. So the last step is I have a diopter power here. Now I can find out the focal length of that by just taking the reciprocal of that number. So the focal length is then equal to 1 divided by a positive 75. And that will equal positive 1.33 repeating meters. So a much longer focal length on the right side than I have the entering, because I have a weaker lens. I started out with a little bit stronger lens here. So where does that light come to a focal point? 1.33 meters to the right of the lens. And the reason that it doesn't have a focal point of just the 2 diopter lens is because we have this light source that's closer to the lens. We no longer have parallel light striking the lens. This is Basic Optical Concepts, Unit 3, Divergence Problem Demonstration. Here's the problem. We have a light source that is 50 centimeters to the left of the lens, and the focal point is 40 centimeters to the right. What is the power of the lens? First of all, let's draw in what we do know. Let's sketch this out. It's helpful if you have a picture. So we have a light source here, and light rays always diverge from their source. And we know that is 50 centimeters to the left of some lens. And we don't know what that lens is. That's our task, is to find out that power. We also know that we have a focal point over here, 40 centimeters to the right of the lens. We know that this is positive because it's to the right. So my guess is we're going to have some kind of positive lens here that is influencing the fact that we have a positive focal point. And we know that this is negative because this is to the left of the lens. And we know that we can consider both of these focal lengths, from the lens to the light source and from the lens to the focal point, actually. So I need to have these values, both of these values in meters, because my focal length and diopter problems require that. So let's convert that first of all to half a meter and positive 0.4 meters. I can find out what the diopter power of the light is entering the lens, because that's my typical step 1. Diopter power enter is equal to 1 divided by the focal length. And I can find out what my diopter power exiting is, because I know diopter power exit is equal to 1 over the focal length, or just taking that reciprocal of that number. So let's do that part. We've got 1 divided by a negative 0.5. Remember, I have to use the meters value here. And that's going to equal a negative 2. And then my diopter power exiting is 1 taking the reciprocal of that, so 1 divided by 0.4. And that's going to equal positive 250 diopters. We'll put diopter powers there. So the light's coming in at a negative 2 diopter strength, but it's leaving at a positive 250 strength. My last thing that I can do is I can use my middle equation. I have this equation that says diopter power enter plus diopter power lens equals diopter exit. So I can do minus 2 plus D equals plus 250. The important part of using this equation is it always has to be in this order. Diopter power enter plus the lens equals the diopter power exit. We can't change that around. But we still can solve it, we just have one unknown now. So here I have a minus 2 that I have to move over to the other side. I just add 2 to both sides of this equation, and I end up with D equals positive 450. So this lens must be positive 450 diopters.